Hi all, I'm Natalie Kalina, and I'm going to talk about our paper, Dynamic Weighted Matching with Heterogeneous Arrival and Departure Rates. So what is dynamic matching? Dynamic matching is a matching problem where instead of having all the information at once, you have agents that are arriving and departing, and you can only match agents, in this case represented as nodes, if they are in the market at the same time. So one can imagine a lot of really good applications for this. So there's a lot of real-world examples of matching where there's a lot of uncertainty about who's in the market at any given time and fluctuation as to who's in the market. So for example, in kidney exchange, you'll have different people who need kidneys at any given time. You have ride sharing, where you might have someone who wants a ride at a particular time, but they might leave the system after a certain amount of time because they may no longer want a ride. They might get a ride from another platform. You have Google AdWords matching ads from sellers to buyers. These people that want ads, it will change over time. The people wanting to sell ads will change over time. So in all of these cases, it's really important to consider not just optimizing matches, but thinking about what you have to do given that things might change in the future. So to go back and clarify, in our case, we're specifically looking at a dynamic matching model where the departures are undeclared. So we can imagine, again, going to these motivations, that in many different motivations, you're not going to have someone say, oh, by the way, this is your last chance. I'm about to leave the system. We're going to have the departure just happen undeclared. There has been a lot of previous work in online matching, the idea of having to solve a matching problem when there are nodes arriving online and you have to make decisions irrevocably. So for example, the seminal work by Karp on this and later work on stochastic versions of that. Maybe more relevantly to our work is Ashalagi's paper on dynamic weighted matching with departure warnings. So here, very similar to our paper, they're looking at not just one side of a graph coming in, but having all nodes within a graph arriving and departing from a system and having to match them while they're there. And they get a constant approximation, but in their case, they're looking at announced departures. So they allow the nodes to declare that they're going to leave before they leave. In this case, they're able to get their solution by taking action when those departures are declared. So in our model, we don't allow this. Most relevantly in terms of related work was an independent and concurrent work that was done by Awad just this year. And in this work, they studied a very similar model where, like us, they're looking at weighted matching with nodes that can arrive and depart and where the departures are unannounced. Their algorithm is guided by a quadratic program and gets a 4e over e minus 1 approximation. By contrast, our algorithm is guided by a linear program, as I'll get into, and it gets a 1/8 approximation, but which is a little weaker, but which has actually been improved in work after the acceptance of this publication to 1/6. Okay, so what exactly is our model? So our model is weighted matching where you have some X, which is the type space of agents. We have different nodes arrive into our system of different types, and the arrival rate will be determined by the particular type. So some type X is arriving with Poisson distribution of rate lambda X. And every single node in the system will depart with departure rate some mu X. And finally, like everything else, the matching rate is determined by the type. So any two given types, if you match, you will get match weight Vxy, where X and Y are the types. And let me also say that our model works for general graphs, not just by part type. So our result is that we develop an online match algorithm, and this algorithm gets a 1/8 approximation of the best in hindsight policy. So of course, if you were able to just say, oh, I will wait and see what all the information is before I make my decisions, then you could do very well. Online matching is, of course, much harder because you have to make decisions before you know that they're the best. Maybe you match two types, but later you realize, oh, I really wanted to match with this other arriving type that's much better. So it's great that we can get this approximation to what the optimal would be. And as I mentioned before, in continuing work that's happening right now, this has actually been improved to 1/6. So now let me give a little intuition for this model. I think it's useful to think about the nodes that are actually in the system at any given time as being organized into buckets of their types. So here we have some nodes that are waiting, that haven't matched yet, but also haven't left yet. They're waiting around of these different types here. And now we have some node arriving, right? So two things could happen. This node could match with a node that arrived previously. Here we see it's matched to this node that's of type T3. And then we would get some value. Or it could wait in the system and it could hope to match to a node arriving later, right? So if it was matching immediately, we would think, oh, this is a really great match. Let's just do this. But of course, you have to balance that with the tension of maybe something really good will arrive later. Of course, if you're waiting, then it's possible that any of these types might leave. So blue might leave before something good comes along. Okay, so how do we get to our solution? In a process that will sound familiar to many of you, we began by creating an LP-based upper bound. And then from there, we use the solution as LP to guide an online matching policy. Finally, we were able to show that this policy in fact got a 1/8 approximation to the LP upper bound, and therefore a 1/8 approximation to the best that we could possibly get in hindsight. Now let me show you this LP that I mentioned just now. It might look complicated, but let's step through it because it's really important in understanding how we solve this problem. If you see here, the actual LP is a summation over all pairs of types. So when we see X, Y, and X, it's all possible pairs of types. And the expression you're seeing there conceptually is saying this is the amount of match value that is contributed to the system by a type Y arriving and matching with a waiting type X. So now let's walk through how it's getting that. So here we have our Y, right? The frequency of arrivals of this type. Now we have alpha XY, the fraction of arrivals of this type Y, which are matching to a pre-existing node of type X. So together, lambda Y and alpha XY are kind of giving you the arrival rate of the event of some node type Y matching to a pre-existing node of type X. And finally, when that's happening, we're getting some value. So that's where VXY comes in. Okay, so maybe you can get a sense of how this is intuitively related to what the value of the matching would be in our model. Now let's look at these constraints. So constraint 1 is bounding alpha XY. So the intuition here is that the matching rate of some arriving Y to a present X can't be higher than the amount of the time that you would expect any node of that type X to be available at all. So, for example, if you expect that some type X is in the system very rarely, say it has a low departure rate, a high departure rate and a low arrival rate, then it is not reasonable that we could possibly expect that our node Y would be able to match to it almost all the time that it arrives. The second constraint is bounding the total match frequency of any particular type. So basically, a type can't match more frequently than it arrives, right? So on the left side here, we have two different summations, and one is saying, okay, this is the total frequency of X matching when it arrives first, and then the second one is the total frequency of matching X when it arrives second. And certainly the frequency of these matches together can't be greater than the frequency of the arrival of X. Finally, we just have that alpha XY, because it is representing a fraction, it must be between 0 and 1. So alpha XY is what we're trying to solve for here in this LP, because we know V, we know lambda for all of our types. And what we're trying to figure out is, given this information in our LP, what would we like the fraction of match rates of each of these types arriving? So in our ideal scenario, if some type Y is arriving, what do we want the probabilities that it's matching to any given other types in the system to be? Okay, so once we have that solution, I'll now describe how we use it in order to form our online match algorithm. So note here I've written out this PXY, which is a probability that we're going to use in this algorithm, and it includes this alpha in it. So say we have this new arrival. We're going to randomly permute the types. So see here we have T1, T4, T3, T2. And then in that permuted order, we will examine all of the types. So the first thing we do, so now we're examining type T1, is we will match to it if it exists at all. First we check, is it present? In fact, it is. We're going to match with the probability of 1/2 times alpha xy times this max term that I'll describe later. So in this case, we have that x is t1 and y is t2. Okay, so say in this case that probability doesn't pan out, and we continue. Now we're going to try to match to this type t4. In fact, there is nothing there, so we're just going to continue. And now we're going to, further on in this line, we're going to try to match this type t3. And this probability is going to be, again, it's going to be derived from this expression below, but it's going to be different this time. It's going to be, because now we're looking at t3, not t1, so the term, basically what the x is in the expression is not different. Okay, so say now, in this case, we end up matching with this probability. Great, they're matched. Now note that if the algorithm had gone through entirely and there had never been a case where this type T2 had ended up matching to any of the types that were present, if all the types had gone through, no matches, then this arriving node would have joined all these awaiting nodes in the system, so it could be available for later arrivals to match to it. Okay, so looking at that algorithm, you might ask, why are we not just using alpha xy as the matching rate? Certainly the LP was giving us a sense that we want to be matching some arriving type y with a certain probability to a certain type x. That's what alpha xy is. Why is that not our matching rate? And the reason is because the LP doesn't take into account the probabilities that that given x is even present when we try to match. So let me give you an example. Consider some type x that has arrival rate 1 and departure rate 1 over epsilon. So this epsilon, right, we can say it's very small, and so this x is departing much, much faster than it arrives. It's essentially a flash in the pan. Now say that we have an optimal solution for this, for some model that has this x, such that for some other type y that's in the set of types, alpha xy equals epsilon. So the probability that x is present at a given time is less than or equal to epsilon. It's almost never there because it departs so fast. So now consider our new algorithm is, let's just, every time this y arrives, we're going to try to match to some type x with probability epsilon. Because x, independently of this matching, is only going to be around most epsilon, the match is only going to be generated with probability epsilon squared for every time that y arrives. And this is not going to get us anywhere near where we need to be in terms of matching these matching rates in our actual algorithm. So we need to scale this match by 1 over epsilon. Right, and so the intuition here is, for types that are extremely rare, that are only there a little bit of the time, you need to be generous and give them a lot of chances to match, because you're often going to be looking to match with them and they won't be there. And this will help you scale to the actual matching fraction you're getting. However, when it's a type that's commonly there, when its departure rate is much lower than its arrival rate, for example, we are not actually looking to decrease that, because now we're just saying, because we expect it to be there, we can comfortably hit our matching rate just by matching with a frequency that we've been given in the algorithm. So that's why we end up with this interesting max of 1 and the departure rate over the arrival rate. Because we only care about scaling when it actually has a much higher departure rate than an arrival rate. Okay, so now let's talk about the connections between this opt and then some value you might get by actually running online match. So if we go back to op of LP upper bound, right, the idea was that for every single XY pair of types where we have our Y arriving second, we're looking at the value imbued to the final match. Of all the times that we have Y arrive second and match to our waiting X. And this alpha XY lambda Y is capturing the rate of some event where Y is arriving and matching to our waiting X. Now, we can translate that into the way we think about this expectation of online match. You're going to have some event in which you have a type Y arriving and matching to an X that is present in the system. And for each of those, if we just multiply it by V of XY, we're going to get the expected value that we're going to get over the time window of our algorithm. So we would like to just show that in the way that we are running online match, the lambda xy is similar to alpha xy lambda y, right? We want to show that we're getting these matching rates similar to the LP upper bound. Okay, so let's think a little bit about how that works. I'm not going to give you a full proof, but I want to give you some intuition as to why this is tricky and the types of strategies we use to get to the answer. So, what are the failure cases for some blue type matching to a weighting red? Here I'm trying to think about how I might get a lower bound for some lambda red blue, right? I want to be able to bound that and say, oh, it's pretty close to alpha. What are the things that could go wrong in trying to make this match happen? So first of all, it could match to something else, right? We have these randomly ordered types. So blue could examine some other type before examining this red type, and it could match to it. Another problem is there could be no red types present when the blue arrives, and then no matter what else happens, they're certainly not going to match. Furthermore, it could be that this probability check fails, right? We said we would match with this particular probability, won't always happen. So note that the first two cases are not independent of each other. This is tricky because if they were all independent, that would be great. We could just calculate the probability and the frequency of this event happening by looking at all the probabilities of the failure cases and working that out. But unfortunately, failure case 1 is dependent on the presence of particular types in the market, because of course, going back, if T1, if there were no green types, then we wouldn't have had to worry about that event of it matching with a green type instead of a red type. And the second case also has to do with presence of types in the market because it has to do with the presence of red types. And of course, the presence of red types and green types may well be correlated because maybe they really like to match to each other. So we have to think about how we can upper bound these failure events in a way that makes them independent and ensures that we still have enough of a success probability that we're getting a reasonable expectation. One way that one might think about this is, say that this first failure case, the blue matching into some other type that's not the red type we'd like it to match to, we can upper bound this by something that is independent of the probability of the red types being there, right? So say that we allow the blue to match to not just the green types that it technically should be able to match to, but also green types that are already matched, but just haven't left yet. So say that we pretend that if some green type in our system is matched, until it actually leaves according to its Poisson departure process, it's still available to match. So now think about what this failure case is. First of all, this is definitely an upper bound on the failure before. Now we're saying blue could get distracted not just by the actually present green types, but also by ones that it really shouldn't be able to match to. But now this event is actually independent of the match rates in our system because it just depends on the arrival and departure rates of the type T1 according to the Poisson process. And this is independent of everything else, and therefore you can maybe see how we're able to use this to tease apart these failure cases and then actually construct a real probability. Another technique that we employ to get our approximation is introducing slack to the system. So note here we have this expression I've shown before, this probability that we're using in our algorithm. And we talked about the alpha, we talked about the max, but we haven't talked about the 1/2. So this 1/2 is allowing us to have a guaranteed, with pretty good probability, that we will have types in the system at any given time to take advantage of matches that are really good. So note that by having this 1/2, we're making it more likely that when some type arrives and tries to match to all weighting types, it's going to end up deciding not to match any of them, even if they're there, and just decide to wait in the system itself. And this slack is designed to help deal with this failure case too, that there's no red types present, right? So we want to have some guarantee that, in fact, we have a pretty reasonable chance of there being a red type present, so that when this blue is arriving, we're matching with the red type a lot of the time. So let's summarize what we've gone through. So first I discussed that we created an LP-based upper bound. Then we use this solution to our LP to guide our matching policy. And finally, we looked at the similarities between the LP and the policy and were able to derive a conclusion that this policy is actually a 1/8 approximation of the upper bound. And then, of course, it's a 1/8 approximation of the optimal in hindsight for the LP. Thank you so much for your attention.